Section: Contents. In this section, we introduce the International Mathematical Olympiad, (IMO), a highly regarded math competition for high school students globally. The problems presented at the IMO are notably challenging, requiring a profound grasp of mathematical concepts and creative application. Among the 4 categories of IMO problems, geometry stands out as the most consistent and accessible, making it ideal for foundational reasoning research. We identify 2 primary methods for automatically solving geometry problems. The first involves algebraic techniques, such as Wu's method, the area method, or Grobner bases. The second method employs synthetic techniques, including deduction databases and the full-angle method. We concentrate on the latter, as it aligns more closely with human reasoning and facilitates the transfer of research insights to other fields. In our earlier work, we developed AlphaGeometry, AG1, a neurosymbolic system that made significant strides in this area, achieving a 54% success rate on all IMO geometry problems from 2000 to 2024. AG1 integrates a language model with a symbolic engine to effectively address these complex challenges. However, AG1 faced limitations due to the narrow scope of its domain-specific language, the efficiency of its symbolic engine, and the capabilities of the initial language model. To overcome these challenges, we present AlphaGeometry 2, AG2, a major upgrade that significantly improves performance. AG2 utilizes a more advanced Gemini-based language model trained on a broader and more varied dataset. We also introduce a faster and more robust symbolic engine, which includes optimizations like a streamlined rule set and better handling of double points. Additionally, we expand the domain language to cover a wider array of geometric concepts, such as locus theorems and linear equations. To enhance performance further, we develop a new search algorithm that explores a wider range of auxiliary construction strategies and incorporates a knowledge-sharing mechanism to speed up the search process. Our goal is to create a fully automated and reliable system capable of solving geometry problems in natural language. We achieve this by using Gemini to translate problems from natural language into the AlphaGeometry language and implementing a new automated diagram generation algorithm. These improvements lead to a remarkable increase in performance, with AG2 achieving an 84% success rate on all IMO geometry problems from 2000 to 2024. Marking a significant advancement in AI's ability to tackle complex mathematical reasoning tasks, even surpassing the average IMO gold medalist. We also detail key enhancements in AG2, including an expanded domain language that now covers locus-type theorems, linear equations, and non-constructive problem statements. The symbolic engine is stronger and faster, with an optimized rule set and improved handling of double points. Our advanced search algorithm employs multiple search trees with knowledge sharing, and the enhanced language model leverages the Gemini architecture trained on a larger dataset. Initially, AG1 utilized a simple domain-specific language with 9 basic predicates, which covered 66% of geometry problems from 2000 to 2024. However, AG1 could not address linear equations or common problem types like find the angle. AG2 resolves these issues by adding 2 new predicates for questions like find x, one for finding angles and another for finding ratios. AG2 also introduces 3 additional predicates to express linear equations involving geometric quantities. Furthermore, we address locus problems, which involve the movement of geometric objects, through a new predicate syntax. We include explicit predicates for diagram checks to ensure topological and non-degeneracy conditions. By relaxing the constraints on how points are defined, AG2 can now handle more complex problems, improving the coverage of the domain language from 66% to 88% for all IMO geometry problems from 2000 to 2024. The remaining 12% includes 3D geometry, inequalities, nonlinear equations, and problems with an arbitrary number of points. We summarize all problems addressed by AG1 and AG2, noting those not covered as not attempted. Section Summary. In this section, we introduce AlphaGeometry 2, AG2, an upgraded neuro-symbolic system that significantly improves upon its predecessor by expanding the domain language, enhancing the symbolic engine, and implementing a novel search algorithm, resulting in an impressive 84% solve rate on EMO geometry problems from 2000 to 2024. We also detail the new predicates and techniques that allow AG2 to address previously unsupported problem types, thereby increasing its coverage from 66% to 88%. Section: Automated Formalization. In this section, we address the automated formalization process, which is a significant challenge for AlphaGeometry and similar neurosymbolic systems. Currently, we must manually convert natural language problems into a specific domain language. For instance, a simple geometry problem like, given a triangle ABC with two equal sides AB equals AC, prove that angles B and C are equal, is transformed into a more technical format in AlphaGeometry. Automating this formalization is an ongoing research area and is more complex than translating between human languages, as it often requires us to rephrase the original problem and clarify any ambiguities. To tackle this, we utilize a foundation model called Gemini to automate the formalization for AlphaGeometry. We begin by manually translating several geometry problems into the AG language, which we then use to create a few-shot prompt for Gemini. We query Gemini multiple times and combine the results to achieve a final answer. With this method, we successfully formalized 30 out of 39 geometry problems from the International Mathematical Olympiad from 2000 to 2024, showing high accuracy for simpler problems. Next, we discuss automated diagram generation, another manual aspect of our process. In AG1, we define each point using a limited number of basic predicates, allowing for automatic diagram generation. However, in AG2, we can define points with multiple predicates, which helps us address non-constructive problems. For example, in a problem where the incenter of a triangle is defined by additional conditions, constructing diagrams becomes more complex and often requires human input. To automate diagram generation for non-constructive problems, we propose an algorithm that encodes constraints as functions and uses a two-step numerical search. Initially, we apply gradient descent optimization to minimize errors related to these constraints. Once we reach a certain accuracy, we switch to a different method to solve the resulting equations. This two-stage approach improves upon previous methods and allows us to generate diagrams for 41 out of 44 formalized problems efficiently, often within seconds. Finally, we focus on enhancing our symbolic engine, known as DDAR, which is essential for AlphaGeometry. DDAR computes the deduction closure, which is the complete set of deducible facts based on initial information. It does this by applying a set of rules iteratively. Speed is critical for both generating training data and conducting proof searches, as faster processes enable more extensive exploration and better results. We will detail three key improvements to DDAR: its ability to handle double points, a faster algorithm, and a more efficient implementation. Section Summary. In this section, we address the challenges of automated formalization and diagram generation in AlphaGeometry, utilizing the Gemini model to translate geometry problems from natural language into a domain-specific language, achieving high accuracy in formalization. We also introduce a two-stage optimization method for generating diagrams from non-constructive problems, significantly improving efficiency and success rates in diagram creation. Section: Handling double points. In this section, we discuss how we handled double points while re-implementing the DDAR algorithm. Our goal was to maintain a similar logical strength to the original, but we made it slightly stronger by using a more general theorem. However, we noticed that DDAR1 lacks the ability to handle 2 points with different names but identical coordinates, which is essential for solving complex problems. For instance, when we want to prove that the intersection of 2 lines lies on a specific circle, we can reformulate the problem to show that the intersection of one line and the circle lies on the other line. This approach can simplify the proof process. To reformulate reasoning with double points, we follow 4 steps. First, we create a new point as the intersection of a line and the circle. Next, we prove that the original point lies on the second line. Since both points lie on the first line, we conclude they are the same, confirming that the point lies on the circle. Regarding efficiency, the DDAR1 algorithm processes a list of rules and applies them to all point combinations. This involves a candidate search step, which is polynomial in the number of points, and a clause matching step, which is exponential in the number of clauses. The worst-case scenario for searching similar triangles can be very time-consuming. To improve efficiency, we hard-code essential rules, reducing the number of queries significantly. We also eliminate explicit rules for angles and distances, allowing the AR engine to handle those automatically. In AG2, we developed the DDAR2 algorithm, which improves the search for similar triangles by hashing the shapes of point triples. For cyclic quadrilaterals, we hash pairs of points and segments to identify repetitions. The AR module helps track known relationships and simplifies linear expressions. To further enhance speed, we implemented the core computation in C++, resulting in a library that is over 300 times faster than DDAR1. We benchmarked this improvement using a set of challenging problems, finding that DDAR2 completed tasks much quicker than DDAR1. Additionally, we improved our synthetic training data by integrating a language model, which significantly increased our solve rate for selected problems. Our data generation method starts with random diagrams and uses the symbolic engine to deduce facts, avoiding reliance on human-crafted problems. This approach helps us explore a broader range of theorems and continues to enhance our synthetic training data. Section Summary. In this section, we discuss enhancements made to the DDAR algorithm, including the introduction of DDAR2, which improves efficiency by optimizing the search for similar triangles and cyclic quadrilaterals, and implementing core computations in C++ for significant speed gains. We also emphasize the importance of generating synthetic training data from random diagrams to avoid contamination and expand theorem distributions beyond established knowledge. Section: Larger, more complex diagrams and better data distribution. In this section, we discuss our advancements in generating larger and more complex diagrams with improved data distribution. We begin by scaling up our resources for data generation and carefully rebalancing the data distribution. As shown in our figures, AG2 explores random diagrams that are twice the size of those in AG1, enabling us to tackle much more complex problems. We can produce theorems that are up to twice as complex, meaning they involve more points and premises, and we can generate proofs that are up to 10 times more complex, indicating a significant increase in proof steps. Additionally, we achieve a more balanced distribution of data across different question types and between problems with and without auxiliary points. Moreover, AG2 generates a wider variety of theorems. In addition to classic statements like AB equals CD, we also create problems related to locus types, which involve statements about movement, such as, when point X moves along line or circle Y, point Z moves along a fixed line or circle T. Unlike AG1, which lacked the concept of movement, AG2 tracks the movement dependencies for each point during diagram generation using a function that identifies the points controlling the movements. We have also enhanced the speed of our data generation algorithm. In AG1, we performed a deduction closure on random diagrams and then traced back to find the minimal problem and proof for each fact. This process involved exhaustively removing subsets of points, which was inefficient for larger problems. We have now adopted a greedy discarding algorithm that requires only a linear number of checks to determine if a set of points can prove the goal. This algorithm guarantees finding a minimal set of points, provided the checks are monotonic. However, we also need to ensure that the pruned set remains closed under construction dependencies, which complicates the monotonicity. We address this by processing points in a reverse topological order. Additionally, we have developed a novel search algorithm in AG2. Instead of the simple beam search used in AG1, we now run multiple differently configured beam searches in parallel, allowing them to share knowledge. We refer to this as the Shared Knowledge Ensemble of Search Trees, SKEST. In this approach, each node in a search tree represents an attempt at auxiliary construction followed by a symbolic engine run. If successful, all trees terminate. If not, the node records the facts proven by the symbolic engine into a shared database, which can benefit other nodes. We employ various types of search trees to explore the search space effectively. These include the classic search tree from AG1, a tree that predicts multiple auxiliary points at each node, and a tree that predicts different types of auxiliary points uniformly. We also utilize deep but narrow trees and shallow but wide trees to optimize our search process. Section Summary. In this section, we enhance our data generation by scaling up resources, achieving more complex diagrams and proofs, and improving data distribution across question types. We also introduce a faster and more efficient search algorithm, SKEST, which utilizes parallel beam searches and knowledge sharing to explore the search space more effectively. Section: System Design Details. In this section, we outline the system design details. For our proof search, we utilize TPUV4 to manage multiple replicas of each model, allowing different search trees within the same model to access the same server using their unique search strategies. We run these search trees and the language model, LM, workers asynchronously alongside the DDAR workers. The LM workers document the nodes they explore in a database, while the DDAR workers pick up these nodes to work on them. The DDAR workers coordinate to ensure an even distribution of tasks. A single pool of DDAR workers is shared across various problems, enabling those that are solved earlier to free up resources for others still being addressed. Next, we introduce a better language model. The AG1 language model, which is a custom transformer, was trained in two phases, first on problems with and without auxiliary constructions, and then solely on those with auxiliary constructions. For AG2, we streamlined this process to a single phase of unsupervised learning on all available data. Our new language model is a sparse mixture of expert transformer model built on the Gemini framework and trained on AG2 data. We train several models of varying sizes using 3 setups: training from scratch with a custom tokenizer for domain-specific language, fine-tuning pre-trained math-specialized Gemini models in natural language, and multimodal training from scratch that includes an image input of the geometry problem. We create a large synthetic training set of about 300 million theorems and 3 evaluation sets: 1 with and without auxiliary points, 1 with only auxiliary points, and a special set of geometry problems from the International Mathematical Olympiad from 2000 to 2024 that AlphaGeometry has previously solved. All sets include complete proofs, and we calculate perplexity loss during training. However, we note that these are only proxy metrics because, during inference, we only use auxiliary points suggested by the LM, while perplexity is calculated on the entire proof. Additionally, there are multiple ways to solve a problem, but perplexity is based on one specific solution. Our main metric remains the solve rate on EMO problems, where the LM generates auxiliary points followed by a DDAR run through beam search. We train our models with the largest batch size our hardware allows using TPUV4, employing a learning rate schedule that includes a linear warm-up followed by cosine annealing. We determine learning rate hyperparameters based on scaling laws. We illustrate learning curves for different sizes of Gemini models, showing that larger models lead to lower perplexity loss across training, evaluation, and our special EMO evaluation set. For inference, we solve new problems using the search algorithm with multiple search trees and various language models. Unlike AG1, we implement top K sampling with a temperature of 1 and K equal to 32. A higher temperature and multiple samples are crucial for tackling EMO problems. With a greedy decoding approach, our models could only solve 2 out of 26 problems needing auxiliary constructions. By increasing the temperature and using 32 samples without a search tree, we improved the solve rate to 9 out of 26. Lower temperatures do not yield diverse enough auxiliary constructions, while higher temperatures lead to outputs with incorrect domain language syntax. In AG1, the interaction between the LM and DDAR was minimal, with DDAR using auxiliary constructions from the LM until a solution was found. In AG2, we enhance this neurosymbolic interface by informing the LM about deductions made by DDAR before it proposes auxiliary constructions. We provide the LM with three sets of information: the facts deducible by DDAR from the original problem, the facts deducible assuming the goal is true, and the numerically correct facts based on the diagram. We serialize and concatenate these sets into an analysis string using our domain-specific language, which is then fed into the LM along with the original problem statement. In contrast, the input for the AG1 LM was simply the problem statement. Section Summary. In this section, we describe our system design for proof search using TPUv4, where multiple asynchronous search trees and language model, LM, workers collaborate to explore and solve problems efficiently. We also introduce our new language model, which simplifies training to a single phase and incorporates multimodal inputs, while enhancing the inference process through a richer neurosymbolic interface that allows the LM to utilize deductions made by the DDAR workers. Section: Results. In this section, we focus on our main metric, which is the solve rate for geometry problems from the International Mathematical Olympiad, IMO. We have a total of 45 geometry problems from the years 2000 to 2024, which we have converted into 50 AlphaGeometry problems, referred to as IMO AG50. Some of these problems are divided into two parts due to our formalization approach. Our key finding, illustrated in a figure, shows that AlphaGeometry 2 successfully solves 42 out of the 50 problems, marking a significant achievement as it outperforms an average gold medalist for the first time. We provide further details in a table that compares different configurations of AlphaGeometry 2 with other systems like AlphaGeometry 1 and Tong geometry. Additionally, we evaluate a new set of 30 challenging IMO shortlist problems that can be expressed in the AlphaGeometry 2 language and have not been previously featured in the IMO. More information on these results can be found in the appendix. In another figure, we show the solve rate for IMO problems based on the training time, measured by the number of tokens seen during training, for one language model using a classical tree search method. Notably, AlphaGeometry 2 manages to solve 27 out of 50 problems after just 250 training steps, which corresponds to around 200 million tokens. We also conduct ablation studies to see how different inference settings impact performance. For a single search tree, we determine that the best configuration includes a beam size of 128, a beam depth of 4, and 32 samples. Increasing the number of samples or the size of the beam search does not lead to solving more problems. Our geometry experts and IMO medalists have noted that many solutions produced by AlphaGeometry demonstrate exceptional creativity. We include several examples of this in the appendix, along with detailed analyses. Among the unsolved IMO problems, we have 2 that we attempted but could not solve, and 6 that are unformalizable. The unformalizable problems involve inequalities and a variable number of points, which are not currently addressed by the AlphaGeometry 2 language. 2 of the unsolved problems from the IMO, specifically from 2018 and 2023, require advanced techniques like inversion, projective geometry, or radical axis, which are not part of our current system. Although these problems could theoretically be solved without these techniques, doing so would necessitate longer inference times, more extensive proofs, and additional constructions to compensate for the lack of these methods in our current setup, which limits AlphaGeometry's problem-solving abilities.